Hello and welcome to Infinite Science. If you're listening to this now, wherever you are, thank you for being here, for choosing to step away just for a little while from everything else, to drift with us into the quiet darkness, into the places where light takes millions of years to arrive, and where silence is so absolute it becomes something you can almost touch. Tonight, we're going to explore some of the strangest things we have ever found out there, in the space between stars, in the folds of space-time, in the echoes of the universe's first breath. These aren't just mysteries, they're invitations, reminders that reality is far stranger, far more delicate, and far more beautiful than we ever imagined. So settle in, turn down the lights if you can, and let's begin. There are planets that belong to no one. Drifting alone through the galaxy, untethered from any star, they move through the void in perfect silence. We call them rogue planets, though even that name feels too violent for what they are. They are orphans, wanderers, worlds that were born in the chaos of stellar nurseries and then cast out, ejected by gravitational struggles between larger bodies, or perhaps freed when their parent star died. Imagine it for a moment. A planet roughly the size of Earth or Jupiter or something in between, spinning slowly in the dark. No sun to orbit, no light to warm its surface, no seasons, no days. Just the faint radiation of its own dying core and the cold whisper of cosmic background radiation that fills all of space. We've found them. Not many yet, but enough to know they're common. Some estimates suggest there may be billions of rogue planets in our galaxy alone. More planets adrift than planets bound to stars. An entire hidden population moving through the space between constellations like ships without harbors. The discovery of these worlds began with a technique called gravitational microlensing. When a massive object passes between us and a distant star, its gravity bends the starlight, acting as a lens. The star appears to brighten briefly, then return to normal. By analyzing these events, astronomers can detect objects that emit no light of their own. And what they found was surprising. Not just a few rogues, but potentially billions. Some ejected during the chaotic early stages of planetary system formation, when young planets' orbits were still unstable. Others cast out later, when a passing star disrupted their solar system's gravitational balance. Still others may have formed alone, condensing from gas clouds without ever being part of a planetary system. The ejection process is violent. A young planetary system is like a gravitational dance where partners constantly change positions. If one planet gets too close to another, or if a massive gas giant migrates inward toward the star, smaller worlds can be flung outward at tremendous speeds. Fast enough to escape the star's gravity entirely. And once they're out, there in the darkness between stars, they never stop moving. They carry the momentum from their ejection, drifting through the galaxy for billions of years. Some may eventually encounter another star and be captured into a new orbit, but most will wander forever. Some of them may have atmospheres, thick blankets of hydrogen and helium, trapping just enough internal heat to keep their surfaces above the frigid baseline of space. The larger ones, Jupiter-sized worlds, could retain heat from their formation for billions of years. Their cores, compressed by enormous gravitational forces, would generate warmth through slow contraction. Others might harbor subsurface oceans, warmed by tidal forces or radioactive decay, liquid water existing in total darkness beneath kilometers of ice. Could life exist there? It's not impossible. Life on Earth thrives in places we once thought uninhabitable. Deep ocean vents, kilometers below the surface where sunlight has never reached. Organisms that derive energy not from photosynthesis but from chemical reactions in the planet's crust. If biology can begin in such places here, why not on a rogue planet drifting forever through the galaxy's arm? These worlds might have their own ecosystems, utterly divorced from starlight. Chemosynthetic bacteria clustered around hydrothermal vents, perhaps even complex organisms adapted to eternal darkness, living out entire evolutionary histories without ever knowing what a sun looks like. The chemistry would be different, certainly. Energy would be scarce. But life is resourceful. On Earth, organisms have adapted to extreme radiation, crushing pressures, acidic environments, and near absolute zero temperatures. Given billions of years, who can say what might evolve in the dark oceans of a rogue world? There could be entire ecosystems down there. Food chains based on chemical energy rather than sunlight. Predators and prey moving through eternal night. Evolution proceeding in complete isolation, producing forms of life we couldn't imagine. But whether or not they host life, rogue planets remind us of something profound, that belonging to a star, basking in light, following a predictable orbit. These things are not guaranteed. They are privileges, accidents of formation. Most worlds may spend eternity in the dark, alone, and we would never know. And perhaps some of them pass close to us. Every few million years, a rogue planet might drift through the outer reaches of our solar system, invisible, undetected. A silent visitor moving through the Oort cloud like a thought through a dream. We wouldn't see it unless we were looking in exactly the right place, at exactly the right time. Recent surveys using gravitational micro-lensing have begun to census these wanderers. When a rogue planet passes between us and a distant star, its gravity bends the starlight, causing a brief, telltale brightening. By measuring these events, astronomers estimate that rogue planets may outnumber stars in our galaxy. Think about that. More wandering worlds than suns. A hidden majority, drifting in silence. And some may be close. Within a few light years of Earth, there could be rogue planets we have never detected. Dark worlds, moving through the space between stars, invisible to our telescopes unless they happen to pass directly in front of a background star. The thought is both eerie and beautiful, that we are surrounded by invisible worlds, that the space between stars is not empty, but populated by silent wanderers, each with its own history, its own geology, perhaps even its own biology. We might never know they're there. They could pass within a light year of Earth and we'd miss them entirely. No light to reflect, no heat to radiate, just cold, dark spheres drifting through the void. But someday, perhaps, we'll develop better detection methods. Infrared surveys sensitive enough to spot their faint thermal glow, or gravitational wave detectors precise enough to feel their passage through nearby space. And when we do, we might discover that our cosmic neighborhood is far more crowded than we ever imagined. Space, you see, is not just vast. It is overwhelmingly empty. And in that emptiness, entire worlds can vanish. But not everything in space is still. There is something out there pulling. In the direction of the constellations Hydra and Centaurus, roughly 200 million light-years away, there exists a gravitational anomaly so powerful that it influences the motion of galaxies across hundreds of millions of light-years of space. We call it the Great Attractor, though we cannot see it directly. Our galaxy, the Milky Way, is moving. Not just spinning, not just orbiting within our local group, but actually traveling through space at over 600 kilometers per second. And we're not alone. Thousands of galaxies in our region of the universe are all streaming in the same direction, drawn by something massive, something hidden behind the dust and stars of our own galactic plane. For decades, we couldn't see what it was. The Great Attractor sits in a region astronomers call the Zone of Avoidance, a band of sky so thick with the gas and dust of the Milky Way's disk that observations in visible light are nearly impossible. It's like trying to see across a crowded room through a wall of fog. You know something is there because you can feel its influence, but you cannot make out its shape. The discovery began in the 1970s when astronomers noticed something peculiar about the cosmic microwave background. After accounting for Earth's motion around the Sun's motion around the galaxy, and the galaxy's motion within the local group, there was still a residual velocity. We were moving towards something. This was puzzling. If the universe were perfectly uniform, we should see the cosmic microwave background the same in all directions. But we don't. There's a dipole pattern, slightly warmer in one direction, slightly cooler in the opposite direction. This indicates we're moving relative to the background radiation. Eventually, using radio waves and infrared light, wavelengths that can penetrate dust, we began to piece together what lies in that direction. We found a massive supercluster of galaxies, a structure so dense that its combined gravity warps the motion of everything around it. The Norma cluster, the Centaurus supercluster. Hundreds of thousands of galaxies bound together in a cosmic web, their collective mass drawing us gently, inexorably toward them. But even that wasn't the whole story. Because beyond the Great Attractor, we discovered something even larger, the Shapley supercluster, a structure containing more than 8,000 galaxies, one of the densest concentrations of mass in the observable universe. And it too is pulling. Everything within 500 million light-years feels its influence. The mass involved is staggering. The Shapley supercluster contains roughly 10 million billion times the mass of our Sun. Its gravitational influence extends across a significant fraction of the observable universe. We are falling then, not into danger, not toward destruction, but simply falling through space, caught in currents of gravity that began flowing billions of years ago. The universe is not static, it is a river, and we are adrift in it. Our motion is complex. We orbit the Sun orbits the galactic center. The Milky Way moves within the local group, gravitationally bound to Andromeda and a few dozen smaller galaxies. The local group itself is being pulled toward the Virgo cluster. And all of these motions are influenced by the Great Attractor and the Shapley supercluster beyond. It's a cosmic ballet, choreographed by gravity over billions of years. And here is the strangest part. We will never reach it. The expansion of space itself, driven by dark energy, is accelerating. The distance between us and the Great Attractor is growing faster than we can fall toward it. We are caught in a cosmic tug-of-war between gravity, which pulls us closer, and the expansion of space, which pushes everything apart. Eventually, billions of years from now, the expansion will win. The Great Attractor will slip beyond our cosmic horizon, receding faster than light can travel, and it will disappear from our universe forever. Whole superclusters of galaxies, unreachable, unknowable, erased by distance. We are, all of us, living in a brief moment of cosmic history when we can still see these things. When the universe is still young enough, still small enough, that light from distant structures can reach us. But that window is closing. Every second, galaxies slip farther away. Every day, the observable universe grows slightly smaller in content as distant objects cross the threshold beyond which their light can no longer reach us. We are living in an age of maximum visibility, and it is passing. The cosmic horizon is shrinking. Not in absolute terms, but in terms of what we can observe. Galaxies are red-shifting toward invisibility. Their light, stretched by the expansion of space, is fading into the infrared, then into radio wavelengths, then beyond detection entirely. Future civilizations arising trillions of years from now will inherit a lonelier cosmos. They will see fewer galaxies, less structure, less evidence of the universe's history, and they will never know what they're missing. In a very real sense, we are the universe's historians, recording observations that will become impossible in the future, building a catalogue of knowledge that later civilizations, if they exist, will never be able to replicate. Our telescopes are time capsules. Our data archives are preserving information about the universe's structure that will eventually be hidden forever. And then there are the signals. In 2007, astronomers detected something that lasted less than 5 milliseconds. A burst of radio waves, incredibly bright, coming from a point in the sky billions of light years away. The signal was so strong, so concentrated, that in those few milliseconds, it released as much energy as the sun emits in an entire day. Then it stopped. We call these fast radio bursts FRBs. And for years we had no idea what caused them. They appeared randomly, unpredictably, scattered across the sky. Most were one-time events, flashing once and never repeating. Ghost signals from the distant universe, arriving without warning and offering no explanation. The first FRB was actually discovered in 2001, buried in archival data from the park's radio telescope in Australia, but it wasn't recognized as a new phenomenon until the 2007 detection confirmed these bursts were real and recurring. The data was puzzling. The bursts showed a characteristic pattern called dispersion. Lower frequency radio waves arrived slightly after higher frequencies, indicating the signal had traveled through ionized gas. By measuring this delay, astronomers could calculate the distance to the source, and the distances were staggering. Billions of light years. Whatever was producing these signals had to be extraordinarily energetic and extraordinarily brief. 5 milliseconds is almost nothing in cosmic terms. Whatever process generated the burst had to be both violent and precise. The precision is remarkable. For something to emit such a powerful burst in such a short time requires incredible coherence. The entire emission has to be synchronized, all the energy released in a coordinated pulse. This rules out many possible sources, some repeated. In 2012, we found one that pulsed again and again, irregularly, sometimes weeks apart, sometimes months. FRB 121102. A source that kept calling out over and over from a faint dwarf galaxy 3 billion light-years away. This was crucial, because repeating bursts meant the source wasn't being destroyed in the process. It was something that could happen multiple times, something resilient, something we might eventually understand. Theories multiplied. Magnetars, neutron stars with magnetic fields so intense they defy comprehension. Colliding black holes, the death throes of exotic stellar remnants. Some even suggested cosmic strings, hypothetical topological defects left over from the Big Bang. And yes, briefly, whispers of artificial origin, though those were always considered the least likely explanation. The artificial origin hypothesis was never seriously mainstream, but it captured public imagination. Could these be signals from distant civilizations? Beacons, communication attempts? The regularity of some repeating FRBs seemed almost deliberate, almost designed, but the energy requirements ruled it out. No conceivable technology could produce bursts this bright. You would need to harness the entire energy output of a star, focus it into a millisecond-long pulse, and beam it across the galaxy. It was theoretically possible, perhaps, but wildly impractical. And why would any civilization do that? For communication, you'd want a continuous signal, or at least something that repeated predictably. The random, chaotic nature of most FRBs doesn't fit any reasonable communication strategy. We still don't have a complete answer. But we've learned some things. FRBs seem to come from regions of intense magnetic activity. They travel through space for billions of years, their radio waves scattering slightly as they pass through clouds of ionized gas. And by measuring that scattering, we can map the distribution of matter between us and the source. They are, in effect, cosmic lighthouse beams, illuminating the structure of the universe itself. The dispersion measure of an FRB tells us how much ionized material the signal passed through on its journey. And by comparing FRBs from different distances, we can trace the distribution of matter across cosmic history. This gives us a new tool for studying the universe's large-scale structure, independent of traditional methods. Some FRBs have traveled through more ionized gas than others, even when coming from similar distances. This tells us about the density variations in the intergalactic medium, the thin soup of gas that fills the space between galaxies. But the question remains, what could produce such intense, brief bursts of energy? What process, what cataclysm, what mechanism in the universe's machinery generates these pulses? In 2020, we detected an FRB from within our own galaxy. From a known magnetar, a neutron star called SGR 1935+2154. It was the first time we could match an FRB to a specific object, a specific type of star. And it confirmed at least one source: magnetars. Those impossible remnants of supernova explosions, spinning hundreds of times per second, their magnetic fields trillions of times stronger than Earth's, can produce fast radio bursts. The mechanism seems to involve starquakes, shifts in the magnetar's crust that release enormous amounts of magnetic energy in an instant, accelerating particles to near light speed and producing coherent radio emission. The crust of a magnetar is crystalline, harder than diamond, but under stress from the shifting magnetic field, it can crack like ice on a frozen lake. When it does, the energy release is catastrophic. Magnetic field lines snap and reconnect, releasing energy equivalent to thousands of years of the sun's output in a fraction of a second. But not all FRBs are the same. Some come from galaxies so distant, so faint that we can barely resolve them. Some repeat with eerie regularity, pulsing every 16 days, or every 157 days, like cosmic metronomes ticking out rhythms we don't yet understand. One source, FRB 180916, repeats in a precise 16.35-day cycle. For 4 days it's active, producing multiple bursts. Then it falls silent for 12 days. Then the cycle repeats. What could cause such regularity? Perhaps the magnetar is in a binary system, and the pulses are only visible when the star is oriented in a certain way relative to its companion. Or perhaps there's some internal mechanism, some oscillation in the star's magnetic field that operates on this timescale. Another possibility, the magnetar's rotation is precessing, wobbling like a spinning top, and we only see the bursts when the emission cone sweeps past Earth. The 16-day cycle could be the precession period. Another source, FRB 121102, not only repeats but seems to be embedded in a persistent radio source. A nebula or supernova remnant, perhaps, surrounding the magnetar. This gives us clues about the environment these objects inhabit. They may preferentially occur in regions of recent star formation, where massive stars have recently exploded. We don't know yet. And every so often, late at night, in radio observatories scattered across the world, a new one arrives. A flash in the data, a spike in the signal, a whisper from billions of years ago. just now reaching. Us, carrying information we are only beginning to decode. The CHIME telescope in Canada, designed specifically to detect FRBS, now finds several per week. Each one a puzzle. Each one a piece of data to add to our growing catalogue. Slowly, we are building a statistical picture of these phenomena. How common are they? Estimates suggest thousands occur across the sky every day, though most are too far or too faint for us to detect. How diverse? We're finding FRBs with different properties, different energies, different durations, different polarizations. What correlations exist between their properties and the galaxies they come from? Some FRBS come from massive galaxies, others from small dwarf galaxies, some from regions of active star formation, others from quiescent regions. Each new detection adds to the picture, but the picture is still incomplete. Space is not silent. It hums, it pulses, it sings in frequencies we cannot hear without machines. And even then, we are only just learning to listen. There are places in the universe where almost nothing exists. Voids. Vast regions of space, hundreds of millions of light years across, nearly empty of galaxies. If you could stand in the center of one, in some impossible way, and look around, you would see almost no light, no nearby stars, no galaxies within 100 million light years in any direction. Just darkness, and the faint cosmic microwave background, the afterglow of the Big Bang, cooling slowly toward absolute zero. These voids are not truly empty. There is still dark matter, still trace amounts of hydrogen gas, still the occasional lonely galaxy drifting through like a ship lost at sea. But compared to the dense filaments and clusters where most galaxies congregate, voids are deserts, absences, negative spaces in the cosmic web. The largest known void, the Butter's void, stretches 330 million light-years across. If the Milky Way were located in the center of it, we would not have discovered other galaxies until the 1960s. Our view of the universe would have been profoundly different, lonelier. We would have believed for much longer that we were alone. Imagine growing up in a civilization located in such a void. Your astronomers would look out and see almost nothing. A handful of dim, distant galaxies at the very edge of detection. No rich clusters, no grand spiral arms filling the sky. Just emptiness. Your cosmologists would struggle to develop theories of the universe's structure. There would be fewer data points, fewer examples of galactic evolution. Your understanding of cosmic history would be delayed by decades, perhaps centuries, and you might never discover the cosmic microwave background. That faint glow requires sensitive instruments and the knowledge that you're looking for something. If your sky contained almost no galaxies, you might never think to search for such a signal. The philosophical implications are profound. How would such a civilization view its place in the cosmos? Would they believe they were special, chosen, the only life in an empty universe? Or would they feel abandoned, isolated in the dark? Their mythology might center on exile and loneliness. Their philosophy might grapple with questions of purpose in an apparently empty cosmos. Would they be more or less likely to search for other life, knowing how empty their observable universe appeared? But voids are not just empty. They are expanding. As the universe grows, driven by dark energy, the voids grow faster than the clusters. Galaxies are drawn toward the densest regions by gravity, leaving the voids increasingly barren. Over trillions of years, the cosmic web will stretch and thin. The voids will dominate, and the universe will become a lonelier place. Clusters of galaxies will become isolated islands, separated by ever-widening oceans of emptiness. Eventually, in the far future, galaxies outside our local group will recede beyond our cosmic horizon. Their light will no longer reach us. And if any civilizations exist in that distant age, they will look out into the sky and see only their own galaxy, surrounded by eternal darkness. They will have no evidence that the universe is expanding, no evidence of the Big Bang, no way to know that they are living in an aging cosmos, slowly fading. All the knowledge we are gathering now, all the observations we are making, will be impossible in that future. The universe will have hidden its own history. We are living in a unique era, an age when the universe is still young enough to be understood, when light from distant galaxies can still reach us, when we can still see the echoes of creation. But that era is ending, and one day the voids will win. The cosmic web, that beautiful filamentary structure of galaxies and dark matter stretching across billions of light years, is temporary. A phase in the universe's evolution. In the deep future, it will dissolve, and what remains will be isolated pockets of matter, separated by distances so vast that no signal, no light, no information can cross between them. Each galaxy cluster will become its own universe, causally disconnected from all others. And in the deepest voids, in those regions already nearly empty, there may be nothing at all. Just space itself, expanding, cooling, approaching absolute zero. A perfect vacuum, stretching to infinity. Some voids have been mapped in exquisite detail. The KBC void, for instance, in which our own galaxy may reside on the edge. It's smaller than the Bootes void, only about 2 billion light-years across, but its existence has implications for cosmology. If we live in or near a large void, it could affect our measurements of the universe's expansion rate. The Hubble constant, which describes how fast the universe is expanding, has been measured 2 different ways, and the results don't agree. One method uses the cosmic microwave background. The other uses nearby supernovae. The discrepancy is small but persistent. Could it be that we're in a region where expansion is slightly different than average? That our local measurements are biased by our position in a void? It's possible. Living in a void would mean we're in a region of lower than average density. And in such a region, the expansion rate might differ from the cosmic average. Our observations would be systematically biased, leading us to overestimate or underestimate the true expansion rate. This is known as the Hubble tension, and it's one of the most pressing problems in modern cosmology. Either there's something wrong with our measurements or something wrong with our models, or we're living in an unusual location. And it reminds us that even our most fundamental cosmological measurements depend on assumptions about our location and the universe's uniformity. Black holes are not strange because they are rare. They are strange because they break reality. At the center of most galaxies, including our own, there exists a region of space-time so warped, so compressed, that nothing, not even light, can escape once it crosses a certain boundary. We call that boundary the event horizon, the point of no return. Beyond it, the normal rules stop applying. Time dilates. Space curves inward. If you could somehow survive falling toward a black hole, you would experience something impossible to describe in everyday language. As you approach the event horizon, time itself would behave differently for you than for someone watching from a distance. To them, you would appear to slow down, your movements becoming sluggish, your light red-shifting, dimming, until you seem to freeze at the horizon's edge, never quite crossing, fading slowly into darkness. But from your perspective, nothing would stop. You would cross the horizon in finite time, falling faster and faster, and as you did, the universe behind you would accelerate. Millions of years would pass outside in what felt like moments to you. You would watch the stars age and die, galaxies collide, the cosmos evolve, all compressed into the final seconds of your fall. This is called gravitational time dilation, and it's one of the most profound predictions of Einstein's general relativity. Time is not absolute. It flows at different rates depending on the strength of the gravitational field you're in. Near a black hole, time becomes currency. The closer you get, the more slowly it flows. At the event horizon, from an outside perspective, time appears to stop completely. And then, if you survived long enough, you would reach the singularity, the point at the center where all the black hole's mass is compressed into a region of infinite density and zero volume. A place where the equations of physics break down completely, where space-time itself becomes meaningless. We don't know what happens there. Our theories stop working. General relativity predicts a singularity, but quantum mechanics suggests something else must occur. Some unknown process, some deeper structure of reality that we have not yet discovered. Perhaps the singularity doesn't exist. Perhaps quantum effects prevent the complete collapse, creating instead some exotic state of matter we have no name for. Perhaps space-time itself becomes granular at the smallest scales, and the singularity is replaced by a quantum foam, a seething chaos of virtual particles and fluctuating geometry. Or perhaps our entire understanding is flawed. Perhaps black holes are doorways to other regions of space-time, other universes, other dimensions. Perhaps information doesn't disappear when it falls in, but is somehow encoded on the event horizon, preserved in two-dimensional form as a hologram. This is the black hole information paradox, one of the deepest problems in theoretical physics. According to quantum mechanics, information cannot be destroyed. It can be scrambled, diluted, made inaccessible, but the fundamental information content of a system must be preserved. If you know the quantum state of a system at one time, you can, in principle, calculate its state at any other time. But according to general relativity, anything that falls into a black hole is gone forever, lost beyond the event horizon, eventually crushed at the singularity. The information it carried about which particles fell in what order, with what quantum states, is destroyed. These two principles cannot both be true. Something has to give. Physicists have proposed solutions. Hawking radiation, a quantum effect that causes black holes to slowly evaporate, might carry information back out. The process is incredibly slow. Larger black holes evaporate more slowly than smaller ones, and supermassive black holes would take longer than the current age of the universe to disappear. But as a black hole evaporates, it shrinks, and smaller black holes radiate faster. Eventually, in the final moments of evaporation, the black hole releases a burst of energy and vanishes. The question is, does the Hawking radiation carry information about what fell in, or is it purely thermal, containing no information? The holographic principle might encode all the information on the event horizon's surface. This radical idea suggests that everything inside a black hole can be described by information on its two-dimensional surface. Three-dimensional reality would be, in some sense, a projection of two-dimensional information. Or perhaps the interior of a black hole is somehow not separate from the exterior, and the information is never truly lost, just hidden behind the horizon where we can't access it. Stephen Hawking himself changed his position on this. He initially argued that information was destroyed, violating quantum mechanics. Later, after years of debate, he proposed that information might be preserved in subtle correlations in Hawking radiation. He conceded a bet he had made with physicist John Preskill, acknowledging that information probably isn't destroyed after all. The debate continues. We don't know yet. But the search for an answer has led to profound insights into the nature of a space-time, quantum mechanics, and the deep structure of reality. Black holes are not just objects, they are problems. Questions the universe has posed to us, written in the language of gravity and light. And some of them are unimaginably large. At the center of the galaxy, M87, 55 million light-years away, there is a black hole with a mass of 6.5 billion suns. Its event horizon is so large that it would stretch beyond the orbit of Neptune if placed in our solar system. The entire inner solar system would fit inside the event horizon, with room to spare. And in 2019, we photographed it. Not directly. You cannot photograph a black hole. It emits no light, but you can photograph the light around it, the glowing accretion disk of superheated matter spiraling inward, compressed and accelerated to a significant fraction of light speed, glowing so brightly it outshines entire galaxies. And there in the center of that disk, we saw it. A dark circle, a shadow, the absence of light, where the event horizon sits. It was the first time humanity had ever seen the shape of a black hole. The first time we had confirmed visually that these objects exist exactly as predicted. The image required a telescope the size of Earth. The Event Horizon Telescope is not a single instrument, but a network of radio dishes scattered across the globe, from Hawaii to Chile to Antarctica. By combining their observations, astronomers created a virtual telescope with an effective diameter of 10,000 kilometers, achieving resolution fine enough to see the event horizon's shadow. The technique is called very long baseline interferometry. Each telescope records radio waves from the target, along with precise timestamps from atomic clocks. Later, the data is combined, and by measuring the tiny differences in arrival time at different telescopes, astronomers can reconstruct an image with extraordinary resolution. The data processing took years. Petabytes of information, collected simultaneously from multiple observatories, had to be synchronized and analyzed. The signals had to be time-stamped with atomic clocks, accurate to within billionths of a second, then correlated to reconstruct the image. When the final image emerged, it showed exactly what Einstein's equations predicted a century ago. A dark circle, outlined by a bright ring of light, bent by gravity. The photon sphere where light orbits the black hole before either escaping or falling in. The bright crescent on one side is due to Doppler boosting. The material moving toward us appears brighter than the material moving away because its light is blue-shifted and concentrated in our direction. But even that image raises questions. How did such massive black holes form so early in the universe's history? We've found quasars, supermassive black holes actively feeding, that existed less than 1 billion years after the Big Bang. There should not have been enough time for them to grow so large. Yet, there they are, blazing in the infant universe, challenging our models of how structure forms. Black holes grow by accreting matter, gas, dust, stars from their surroundings. But there's a limit to how fast they can grow, called the Eddington limit. As matter falls in and heats up, it radiates energy. If too much matter falls in too quickly, the radiation pressure pushes new material away, limiting the growth rate. Even growing at the Eddington limit continuously, a black hole starting from a stellar mass shouldn't reach billions of solar masses in less than 1 billion years. So how did the early quasars get so big? Perhaps they formed from the direct collapse of massive gas clouds in the early universe, creating black holes of thousands or even millions of solar masses right from the start. Perhaps the first generation of stars was far more massive than we thought, leaving behind black holes hundreds or thousands of times heavier than the Sun. Perhaps black holes themselves can merge, combining to form ever larger objects. Or perhaps dark matter plays a role. Perhaps in the dense cores of early galaxies, dark matter particles annihilated each other, releasing energy that fed the growth of black holes, allowing them to exceed the normal limits. We're still working out the details, and there are stranger things still. Magnetars. Neutron stars spinning hundreds of times per second, their magnetic fields so intense that they warp the quantum vacuum itself. If you were to stand 1,000 kilometers from a magnetar, the magnetic field would be strong enough to disrupt the molecular bonds in your body. You would simply cease to hold together. Actually, you'd face many problems before that. The magnetic field would be strong enough to distort your atoms, stretching electron orbitals into elongated shapes. It would interfere with the electromagnetic forces that hold molecules together. Your nervous system, which relies on electrical signals, would cease to function. These stars are the densest objects in the universe that are not black holes. A single teaspoon of neutron star material would weigh as much as a mountain, roughly 1 billion tons. The matter is so compressed that protons and electrons have merged into neutrons, creating a substance found nowhere else in the universe. Neutron stars are the remnants of supernova explosions. When a massive star exhausts its nuclear fuel, it can no longer support itself against gravity. The core collapses in less than a second, compressing to nuclear densities. The outer layers rebound in a catastrophic explosion. What remains is a sphere of neutrons, roughly 20 kilometers across, with a mass greater than the Sun. And the magnetic fields, they are beyond comprehension. 1 trillion times stronger than Earth's, strong enough to bend the paths of photons, strong enough to create matter from empty space, through a quantum process where the electromagnetic field itself spawns particle-antiparticle pairs. The field is so strong that it affects space-time itself. General relativity tells us that energy warps space, and a magnetic field this intense carries enormous energy density. The space-time around a magnetar is measurably curved by the magnetic field alone. Occasionally, their magnetic fields shift, cracking the star's crust, releasing bursts of energy that we can detect from across the galaxy. In December 2004, a magnetar called SGR 1806-2O released a flare so powerful that it temporarily disrupted Earth's ionosphere from a distance of 50,000 light-years. For 1/10 of a second, it was brighter than anything in the night sky except the moon. The burst saturated detectors on spacecraft across the solar system. It ionized Earth's upper atmosphere, creating conditions similar to the day side even though the burst came from the night side. Satellites experienced interference. Some instruments were temporarily blinded. If satellites had been more vulnerable, if our technology had been less robust, it could have caused widespread damage. If that same flare had occurred from a magnetar 10 light-years away, it might have caused a mass extinction event on Earth. The radiation would have stripped away the ozone layer, exposing the surface to lethal ultraviolet light. Without the ozone layer, UV radiation from the sun would kill surface life within months. The electromagnetic pulse would have induced currents in the ground, frying electronics, causing widespread electrical fires. The sheer energy flux would have heated the upper atmosphere, causing it to expand and potentially stripping some of it away into space. Earth's magnetic field would have been severely disrupted. The charged particles from the flare would have interacted with our magnetosphere, creating aurora visible across the entire planet, even at the equator. Compasses would have spun uselessly. Navigation systems would have failed, and in the long term, the increased radiation might have caused genetic damage across many species, increasing cancer rates, reducing fertility, potentially destabilizing entire ecosystems. We orbit a quiet, stable star in a quiet, stable region of the galaxy. We are sheltered from the universe's extremes. The sun is not prone to super flares. There are no nearby massive stars that might explode as supernovae. No magnetars within threatening distance. No gamma-ray burst sources pointed in our direction. But out there in the dense cores of star clusters near the galactic center, in regions of intense star formation, the cosmos is violent in ways we are only beginning to measure. And we are lucky. Extraordinarily lucky. To exist in a place and time where these catastrophes are distant enough to be observed, but not experienced. The nearest known magnetar is about 9,000 light-years away, far enough to be safe. But if one existed closer, within a few light-years, life on Earth could be in danger. It's a reminder that our planet's habitability depends not just on internal factors, the right atmosphere, the right temperature, the right chemistry, but on our cosmic neighborhood. We need to be far from gamma-ray bursts, supernova, magnetar flares, and other catastrophic events. We are, in a sense, living in a safe zone, a region of the galaxy where catastrophes are rare enough that life can persist for billions of years. And we should be grateful for it. But there are stars that do not stay in their galaxies. Hypervelocity stars. Rogue suns traveling so fast they escape the Milky Way entirely, flung into intergalactic space by gravitational encounters so violent that they achieved escape velocity. The fastest known hypervelocity star, S5-HVS1, is traveling at over 1,700 kilometers per second, fast enough to cross the diameter of Earth in under 8 seconds, fast enough to escape not just our galaxy, but potentially the entire local group. How does a star reach such speed? The most common scenario involves the supermassive black hole at the center of our galaxy. Sagittarius A star, that 4 million solar mass monster lurking in the galactic core, occasionally encounters binary star systems. When a binary star pair ventures too close, the black hole's gravity can capture one star while flinging the other away at tremendous speed. It's a gravitational slingshot of cosmic proportions. The captured star spirals inward, its orbital energy transferred to its companion, which is ejected at speeds exceeding the galaxy's escape velocity. Imagine being a planet orbiting such a star. One moment, you're part of a binary system, orbiting both stars in a complex but stable configuration. The next, you're hurtling through intergalactic space, watching your galaxy shrink behind you. The sky would change gradually. Over millions of years, the Milky Way would appear smaller and smaller. The familiar constellations would shift and blur. Eventually, your galaxy would be just another spiral among many, visible only as a faint smudge of light. And ahead, emptiness, the vast gulf between galaxies. No nearby stars, no rich stellar nurseries, just your star, your planets, and the distant glow of other galaxies millions of light years away. We've found dozens of hypervelocity stars now. Most are red giants or young, massive stars, the types most likely to survive the encounter with Sagittarius A star. But there may be many more we haven't detected. Smaller stars, dimmer stars, traveling through the halo of our galaxy or already beyond it. Some hypervelocity stars may have been ejected by different mechanisms. Supernova explosions in binary systems can fling the surviving star away at high speed. Interactions in dense star clusters can produce similar results, and some may come from other galaxies entirely. The Andromeda Galaxy is approaching the Milky Way at about 300 kilometers per second. In a few billion years, they'll collide. The encounter will scatter stars in all directions, creating hypervelocity refugees from both galaxies. Perhaps there are intergalactic wanderers already, stars ejected from galaxies billions of years ago, drifting through the cosmic voids. Ancient exiles carrying with them the remnants of their home galaxy's chemistry. If any of these stars have planets, and some surely must, those worlds would experience the strangest isolation. Citizens of no galaxy, drifting between superclusters. The night sky nearly empty, save for the faint glow of distant island universes. Would life on such a world feel lonely or liberated? Unbound from galactic constraints, free to chart their own course through the cosmos? We'll probably never know, but the thought lingers. Most of the universe is invisible. We know this not because we have seen what is missing, but because we have seen what it does. Galaxies spin faster than they should. The stars in their outer regions orbit at speeds that, according to the visible mass alone, should fling them into intergalactic space. But they don't. Something is holding them in place. Something with mass. Something that interacts with gravity but does not emit, absorb, or reflect light. We call it dark matter, and it makes up approximately 85% of all matter in the universe. The evidence is everywhere. In the rotation curves of galaxies where stars orbit at constant speed, regardless of distance from the center. In the cosmic microwave background where tiny fluctuations reveal the presence of matter that doesn't interact with light. In gravitational lensing where massive galaxy clusters bend the light from more distant objects, revealing far more mass than we can see. The rotation curve problem was first noticed by Vera Rubin in the 1970s. According to Newton's laws, stars farther from a galaxy's center should orbit more slowly, just as outer planets in our solar system orbit more slowly than inner planets. The orbital velocity should decrease with distance. But that's not what Rubin found. Stars at the edge of galaxies were moving just as fast as stars near the center. The rotation curves were flat, not declining. The only explanation was invisible mass. A lot of it, spread throughout and beyond the visible galaxy, providing the extra gravity needed to hold those fast-moving stars in orbit. At first, astronomers looked for ordinary matter they might have missed. Dim stars, brown dwarfs, black holes, planets, cold gas. But no combination of ordinary matter could account for the discrepancy. There simply wasn't enough visible material in any form to explain the observations. We have mapped its distribution by observing how it bends light from distant galaxies, a phenomenon called gravitational lensing. Massive objects warp spacetime, and light follows the curvature of spacetime, so its path bends near massive objects. We have measured its influence on the cosmic microwave background, the faint radiation left over from the Big Bang. The tiny temperature fluctuations in the CMB depend on the ratio of dark matter to ordinary matter in the early universe. By measuring these fluctuations precisely, we can determine how much dark matter there is. We have watched galaxy clusters collide and seen how their dark matter halos move independently of the visible gas and stars. The Bullet Cluster is perhaps the most striking example. Two galaxy clusters collided at speeds of millions of kilometers per hour. The hot gas, which makes up most of the ordinary matter, slammed together and slowed down, emitting X-rays as it heated. But the dark matter passed right through, unaffected by the collision, continuing onward. By mapping the gravitational lensing, astronomers could see where the mass actually was. And it wasn't where the gas was. It was ahead, where the dark matter halos had traveled. Clear evidence that dark matter exists and behaves differently from ordinary matter. The collision stripped the gas away from the dark matter, providing a rare glimpse of dark matter's distribution independent of ordinary matter. But we have never detected a single particle of it directly. Experiments deep underground, shielded from cosmic rays, search for dark matter particles passing through detectors. The idea is that if a dark matter particle collides with an atomic nucleus in the detector, it will produce a tiny flash of light or heat that can be measured. These experiments sit in mines or tunnels, beneath kilometers of rock. The rock shields them from cosmic rays, which would otherwise overwhelm the detectors with false signals. They use ultra-pure materials cooled to near absolute zero, monitored by exquisitely sensitive instruments. And they wait. For years they've been waiting, accumulating data, looking for the telltale signature of a dark matter collision. So far, nothing conclusive. We don't know what it's made of. We don't know if it's made of one type of particle or many. We don't know if it interacts with itself, if it can clump together in structures smaller than galaxies, if it has any properties beyond mass. Candidates include WIMPs, weakly interacting massive particles, axions, sterile neutrinos, and more exotic possibilities. Each has different properties and would require different detection methods. WIMPs would be heavy particles, perhaps tens or hundreds of times the mass of a proton, that interact through the weak nuclear force and gravity. Axions would be ultra-light particles, billions of times lighter than an electron, proposed to solve certain problems in particle physics. Sterile neutrinos would be heavy cousins of ordinary neutrinos, interacting only through gravity. Each candidate requires different experiments to detect. WIMP detectors look for nuclear recoils. Axion detectors look for their conversion into photons in strong magnetic fields. Sterile neutrino. Searchers look for subtle anomalies in neutrino experiments. For all we know, dark matter particles could be passing through your body right now. Billions of them every second, interacting with nothing, ghosting through ordinary matter like it isn't even there. You are transparent to dark matter. It flows through you, through the earth, through the sun as though you weren't there. Only gravity notices its passage, and then there is dark energy, even stranger, even more pervasive. In 1998, astronomers observing distant supernovae made a discovery that defied expectation. The universe's expansion was not slowing down, as gravity should cause it to. It was accelerating. Galaxies were moving away from each other faster now than they were billions of years ago. The discovery was so unexpected that the teams initially thought they'd made an error. They checked and rechecked their data. They looked for systematic biases, dust absorption, evolution of supernova properties, gravitational, lensing, any effect that might mimic acceleration. But the result held. The universe is accelerating. Something was pushing space apart. Some unknown energy, evenly distributed throughout the universe, counteracting gravity on the largest scales. We call it dark energy, though the name is more placeholder than explanation. We don't know what it is. We don't know where it comes from. We don't know why it has the density it does, or why it seems to be constant over time. The simplest explanation is the cosmological constant, a term Einstein added to his equations of general relativity. He later called it his greatest blunder, but it turns out the universe needs it. The cosmological constant represents the energy of empty space itself, a vacuum energy that pushes space apart. But we don't know why it has the value it does. Quantum field theory predicts vacuum energy should exist, but the predicted value is off by a factor of 10 to the power of 120. That's not a typo. 120 orders of magnitude. It's the worst prediction in the history of physics. Something is cancelling out almost all of the vacuum energy, leaving just the tiny amount we observe. But what? And why does it cancel out so precisely, leaving exactly the amount needed to accelerate the universe's expansion? We don't know. But we know it's real, and we know it dominates the universe's energy budget. Approximately 68% of everything that exists is dark energy. Ordinary matter, the atoms that make up stars and planets and you, accounts for less than 5% of the universe's total content. Dark matter is about 27%, and dark energy is the rest. We are not just rare, we are statistically negligible. And the presence of dark energy means the universe will continue expanding forever, accelerating. Galaxies will drift apart, stars will exhaust their fuel. The cosmos will grow cold and dark. Trillions of years from now, in the deep future, the universe will be a vast, empty expanse with occasional lonely stars drifting through the void, slowly fading. This is sometimes called the heat death of the universe, or the Big Freeze. A scenario where entropy reaches its maximum, all usable energy is exhausted and nothing can happen anymore. No stars form, no planets coalesce, no life arises, just cold, dark, empty space expanding forever. The last stars will burn out in about 100 trillion years. After that, only black holes will remain, slowly evaporating through Hawking radiation. The largest black holes will take a Google years to evaporate. That's 10 to the power of 100 years, a number so large it's almost meaningless. And after that, just empty space, expanding, cooling, approaching absolute zero. A universe in thermodynamic equilibrium, a state of maximum entropy where nothing can ever happen again, unless we're wrong about something fundamental. Dark matter and dark energy could be placeholders for physics we don't yet understand. Our equations could be incomplete. Gravity could behave differently on cosmic scales. The universe could be more complex, more layered than our current models suggest. Some physicists propose modifications to general relativity that might explain cosmic acceleration without dark energy. MOND, Modified Newtonian Dynamics, attempts to explain galaxy rotation curves without dark matter, though it struggles to explain other observations like the bullet cluster. Others suggest dark energy is not constant but changes over time, potentially leading to different outcomes for the universe's fate. If dark energy were to decay or disappear, the expansion might slow or even reverse. If it were to strengthen, it might eventually tear apart galaxies, stars, planets, even atoms themselves in a big rip. We are mapping the cosmos with instruments that can only detect 5% of what's there. The rest is inference, shadows, footprints left in the fabric of space-time. We are, in a very real sense, still living in the dark. And yet, we continue searching, building better detectors, launching more sensitive satellites, analyzing data with greater precision. Because even if we cannot yet see what dark matter and dark energy are, we can measure their effects. And from those measurements, we can learn. Slowly, carefully, we are piecing together a picture of the universe. Not the universe as we wish it to be, but the universe as it actually is. Strange, mostly invisible, governed by forces we don't yet understand. And in that strangeness, in that mystery, there is beauty. The universe is teaching us humility, reminding us that what we see is not all there is, that our senses, evolved for survival on an African savanna, are inadequate for perceiving the full reality of the cosmos. We are learning to see with new eyes, mathematical eyes, instrumental eyes, learning to detect the invisible through its influence on the visible. And perhaps, someday, we'll understand. But there are places where even darkness seems strange. The Boomerang Nebula, a cloud of gas and dust about 5,000 light-years away, holds the record for the coldest known place in the universe. Its temperature is approximately 1 degree Kelvin, just 1 degree above absolute zero. Colder than the cosmic microwave background, colder than the ambient temperature of space itself. How is that possible? The nebula is the result of a dying star shedding its outer layers. As the gas expands outward, it cools, and because it is expanding so rapidly, roughly 600,000 kilometers per hour, it has cooled below the temperature of the surrounding space. This is the same principle used in refrigeration. When a gas expands, it does work against external pressure, and that work comes from its internal energy, causing the temperature to drop. It's called adiabatic cooling. In the Boomerang Nebula, this expansion has been so rapid and sustained that the temperature has plummeted to nearly absolute zero. In effect, the universe has created a natural refrigerator. A dying star in its final act has produced the coldest known environment in the cosmos. If you could somehow be transported there, protected from the vacuum, you would be standing in the coldest environment the universe has ever produced naturally. And yet, even at 1 degree above absolute zero, the atoms in the nebula are still moving, still vibrating. Quantum mechanics ensures that nothing ever truly stops. Even at the lowest possible temperatures, uncertainty remains. Motion persists. This is called zero-point energy. Even at absolute zero, particles retain a minimum amount of kinetic energy due to the Heisenberg uncertainty principle. If a particle were completely at rest, we would know both its position and momentum exactly, which quantum mechanics forbids. So even in the Boomerang Nebula, even at temperatures colder than anywhere else in the natural universe, atoms still jitter, still move, still obey the quantum rules that govern all of reality. Absolute zero is unreachable, a limit you can approach but never touch. The third law of thermodynamics states that you cannot cool something to absolute zero in a finite number of steps. You can get close, arbitrarily close, but you can never quite reach it. Each successive step removes less heat than the last. The process becomes asymptotic, approaching zero but never arriving. The universe forbids perfect stillness. But we have created colder. In laboratories on Earth, physicists have cooled atoms to temperatures measured in billionths of a degree above absolute zero. Temperatures colder than anything naturally occurring in the universe. Using laser cooling and magnetic traps, they slow atoms to a near standstill, creating exotic states of matter that exist nowhere else. Bose-Einstein condensates where thousands of atoms occupy the same quantum state, behaving as a single quantum object. In these condensates, quantum effects become visible at macroscopic scales, matter waves, interference patterns, phenomena that normally exist only at atomic scales, blown up to where we can observe them directly. It's a reminder that the universe's extremes are not always natural. Sometimes they're manufactured. Sometimes the strangest physics occurs in carefully controlled laboratories, where human ingenuity pushes matter to conditions it would never experience in nature. On the opposite extreme, there are places of unimaginable heat. When two neutron stars collide, they briefly produce temperatures exceeding 1 trillion degrees. Hot enough that matter breaks down into a quark-gluon plasma, the same state that existed microseconds after the Big Bang. The impact generates a kilonova, a burst of light and radiation that forges heavy elements like gold, platinum, and uranium. Every gold atom on Earth, in every ring, every coin, every circuit board was born in such a collision, billions of years ago, scattered into space, and eventually incorporated into the dust cloud that formed our solar system. We are made of star stuff, as Carl Sagan said, but more specifically, we are made of the rarest star stuff. the elements created not in ordinary stellar furnaces, but in the most violent events the universe can produce. Hydrogen and helium were forged in the Big Bang itself, in the first few minutes of the universe's existence. As the universe expanded and cooled from its initial state, protons and neutrons combined to form the first atomic nuclei. About 75% hydrogen, 25% helium, with traces of lithium. Carbon, nitrogen, oxygen, and lighter metals like iron were created in the cores of stars through nuclear fusion, then dispersed when those stars died. The fusion process builds heavier elements from lighter ones, releasing energy, but it stops at iron. Fusing iron costs energy rather than releasing it, so stars cannot make heavier elements through normal fusion. But elements heavier than iron cannot be created through normal fusion. They need the intense heat and density of supernova explosions or neutron star collisions to form. Processes called rapid neutron capture, where atomic nuclei are bombarded with neutrons so quickly that they build up into heavy elements before they have time to decay. Gold, platinum, uranium. These elements are literally rarer than starlight. They exist because the universe occasionally becomes violent enough to create them. And we've witnessed one. In August 2017, gravitational wave detectors felt a ripple in space-time, a signal consistent with two neutron stars spiraling together and merging. The LIGO and Virgo detectors in the United States and Italy picked up the signal within milliseconds of each other, allowing astronomers to triangulate its position on the sky. Within seconds, telescopes around the world turned toward the source. And there it was, a new point of light in the galaxy NGC4993, 130 million light-years away. For the first time, humanity witnessed a cosmic event both through gravitational waves and through light. Multi-messenger astronomy, we call it. Observing the universe through multiple channels simultaneously. We watched it brighten, then fade over the course of days and weeks. We measured its spectrum and saw the signatures of freshly formed heavy elements. Spectral lines corresponding to gold, platinum, uranium, and other heavy atoms, glowing in the expanding debris cloud. The amount of gold produced in that single event was staggering. Estimates suggest several Earth masses of gold were created, more gold than exists in the entire solar system, flung into space at a significant fraction of light speed. We confirmed for the first time that neutron star collisions are responsible for producing much of the universe's gold and platinum. It was a moment of profound connection, a direct observation of the process that made the atoms in our bodies. We are, quite literally, the children of colliding stars. The event released more energy in a fraction of a second than the sun will emit in its entire 10 billion year lifetime. It sent gravitational waves rippling through space-time at the speed of light, stretching and compressing the fabric of reality itself as they passed through Earth. The waves were incredibly tiny. By the time they reached Earth, after traveling for 130 million years, they stretched and compressed space by less than the width of a proton. An amount so small it seems impossible to measure, but our detectors were sensitive enough to feel it. LIGO uses laser interferometry to measure changes in the lengths of 4-kilometer-long arms. When a gravitational wave passes through, one arm briefly becomes longer, while the other becomes shorter. The difference is minute, but measurable. We detected those waves, felt the universe's fabric vibrate, and in doing so, confirmed one of the last major predictions of Einstein's general relativity. Gravitational waves had been predicted for a century but never directly detected until 2015, when LIGO observed two black holes merging. The 2017 neutron star collision was different. It produced both gravitational waves and electromagnetic radiation, allowing us to study the event across multiple channels. Gamma rays arrived first, within seconds of the gravitational wave detection. Then X-rays. Then ultraviolet and visible light. Then infrared as the debris cloud expanded and cooled. Each wavelength told a different part of the story. We are not separate from the universe. We are a way the universe examines itself. Stardust, contemplating stars. And then there are the planets. Thousands of them now discovered orbiting distant stars. Exoplanets. Worlds so different from our own that they challenge every assumption we once held about what a planet could be. There is HD 189733b, a gas giant where the rain is made of molten glass. Sideways. Driven by winds exceeding 7,000 kilometers per hour, fast enough to circle the planet in less than a day. The planet's deep blue color, which might seem inviting, comes from silicate particles in the atmosphere scattering light. A hostile, beautiful hell. The planet is tidally locked to its star, meaning one side always faces the star while the other side remains in eternal darkness. The temperature difference between day and night drives winds of incredible speed, carrying clouds of vaporized silicate across the terminator line. The day side reaches temperatures of over 1,000 degrees Celsius, hot enough to melt glass. The silicate in the atmosphere vaporizes on the day side, then condenses on the cooler night side, forming molten glass droplets. But before those droplets can fall, the winds catch them, carrying them horizontally at thousands of kilometers per hour. Imagine a rainstorm where the drops move sideways faster than any hurricane on Earth, where the rain is made of molten glass, glowing faintly from its own heat. There is 55 Cancri A, a world that might have a surface partially composed of diamond. A super-Earth orbiting so close to its star that its year lasts only 18 hours. Tidally locked, one side always facing the star, the other in eternal darkness. Temperatures on the day side exceed 2,000 degrees Celsius. The night side is far cooler. Between them, a permanent twilight zone where the physics of carbon under extreme pressure might create structures we can barely imagine. The planet's composition is unusual. Spectroscopic analysis suggests it has far more carbon than oxygen, the opposite of Earth. On our planet, most carbon binds with oxygen to form carbon dioxide, water, and silicate minerals. But on a carbon-rich world, the chemistry would be completely different. Carbon, under extreme pressure and temperature, forms diamond. Deep in the planet's interior, conditions might be right for vast diamond deposits. Perhaps an ocean of liquid carbon with diamond icebergs floating in it. Perhaps layers of the planet's mantle composed entirely of crystallized carbon. We cannot confirm this yet. The planet is far too distant, too small, too close to its star for detailed observations. But models of its interior are consistent with diamond layers comprising perhaps a third of the planet's mass. A world made of treasure by human standards, utterly worthless because we could never reach it. And even if we could, bringing back significant quantities of diamond would crash the market, making them as common as quartz. There is WASP-12b, a planet being slowly consumed by its star. Stretched into an egg shape by tidal forces, its atmosphere is being stripped away, funneling into the star's gravitational well. In 10 million years, it will be gone, devoured. A world with a deadline. The planet orbits so close to its star, closer than Mercury orbits the Sun, that tidal forces are tearing it apart. The star's gravity pulls harder on the near side than the far side, stretching the planet into an elongated shape. Simultaneously, the star's intense radiation heats the atmosphere to thousands of degrees, causing it to expand and escape. The planet is literally bleeding atmosphere into space, forming a vast cloud that spirals into the star. WASP-12b is losing approximately 6 billion tons of mass every second. That's roughly the mass of Mount Everest. Every second, forever. At this rate, the entire planet will be consumed in roughly 10 million years. We are watching a world die in real time. Or rather, we're watching it die as it was 1,200 years ago, when the light we now see left its surface. By now, in the present moment at WASP-12b, the planet may have already shrunk noticeably. Or perhaps it's been destroyed entirely and we won't know for another 1,000 years. And there is Kepler-16b, a planet orbiting 2 stars, a real-life Tatooine. If you stood on its surface, you would see 2 suns in the sky, rising and setting at different times, casting double shadows. Binary star systems are common in our galaxy. Perhaps half of all stars exist in binary or multiple star systems. But for a long time, astronomers believed planets couldn't form in such systems. The gravitational dynamics seemed too chaotic. A planet forming in a binary system has to contend with 2 gravitational sources, each pulling in different directions as they orbit each other. The orbits seem too unstable for planets to survive. Kepler-16b proved otherwise. It orbits both stars in a stable configuration, far enough out that it's affected by their combined gravity rather than being torn between them. Its orbit is stable over millions of years. The view from Kepler-16b would be extraordinary. The 2 suns orbit each other every 41 days, appearing in the sky as a binary pair. Sometimes they eclipse each other, sometimes they're on opposite sides of the sky. Sometimes they rise and set together, sometimes separately. Shadows would be complex. Sometimes you'd have 2 shadows pointing in different directions, sometimes 1. The illumination would vary throughout the planet's year as the suns change position, and the climate would be bizarre. The planet receives varying amounts of light depending on the sun's positions. Sometimes both are on the same side, doubling the illumination. Sometimes they're opposite, providing more even heating. The seasonal variations would be far more complex than anything on Earth. We used to think planets were uniform, rocky worlds close to their stars, gas giants farther out, orderly and predictable. But the universe does not care about our categories. We have found hot Jupiters, gas giants orbiting closer to their stars than Mercury orbits the Sun. How did they get there? They likely formed farther out beyond the snowline where ice can exist, then migrated inward through interactions with the protoplanetary disk. We have found rogue planets drifting alone through space, unbound to any star. We have found planets orbiting neutron stars, worlds bathed in lethal radiation. We have found systems with 7 Earth-sized planets, all potentially habitable, all orbiting a single, dim, red dwarf. TRAPPIST-1, that remarkable system, contains 7 Earth-sized worlds, orbiting a star barely larger than Jupiter. 3 of those planets orbit in the habitable zone, where temperatures might allow liquid water to exist. They're so close together that if you stood on one, you'd see the others in the sky. Some appearing larger than the Moon appears from Earth. The star itself is an ultra-cool red dwarf, with a surface temperature of only about 2,500 Kelvin. It's so dim that planets need to orbit very close to receive enough energy for liquid water. The entire system fits within a space smaller than Mercury's orbit around the Sun. The planets are so close that they exert gravitational influences on each other. Their orbits are in resonance. The orbital periods form simple ratios. For every 8 orbits of the innermost planet, the next one out completes exactly 5. Precise gravitational choreography. Imagine the view. Multiple worlds hanging in the sky, close enough to see surface features with the naked eye. Continents, oceans, clouds, weather patterns visible in real time. If life existed on multiple planets in such a system, would they be aware of each other? Would they develop astronomy faster, seeing other worlds so clearly? Would they attempt communication, build spacecraft to visit their neighbors? Or would the proximity breed conflict? Competition for resources across interplanetary space? The first interplanetary war fought between neighboring worlds in the same system? We don't know. But the possibilities are fascinating. And there are stranger worlds still. PSR B1257 plus 12. A pulsar, a rapidly spinning neutron star surrounded by at least 3 planets. Worlds orbiting a stellar corpse bathed in intense radiation from the pulsar's magnetic field. How did they survive? Pulsars are created in supernova explosions. The blast should have destroyed any planets. Perhaps these worlds formed after the supernova from the debris disk. Or perhaps they were captured later. Rogue planets that wandered too close and were snared by the pulsar's gravity. Life there would be impossible by any definition we know. The radiation environment is lethal. The magnetic field strong enough to disrupt matter at the atomic level. But they exist. Planets orbiting a dead star. A reminder that planetary systems can persist even after their star's death. And we have barely scratched the surface. Most of the exoplanets we've discovered are large, because large planets are easier to detect. They block more light when they pass in front of their stars, the transit method. They exert stronger gravitational tugs on their parent suns, causing the star to wobble, the radial velocity method. But smaller planets, Earth-sized worlds, rocky planets with thin atmospheres, are harder to find. They block less light. They cause smaller wobbles. Detecting them requires more precise instruments, longer observation times, more careful analysis. The Kepler Space Telescope, which operated from 2009 to 2018, discovered thousands of exoplanets by staring at a single patch of sky and watching for transits. When a planet passes in front of its star, the star's brightness dims slightly, typically by less than 1% for an Earth-sized planet. By measuring these tiny dips repeatedly over years, astronomers can determine the planet's size, orbital period, and sometimes even properties of its atmosphere. If the planet has an atmosphere, starlight passing through it will be absorbed at specific wavelengths, creating a spectral signature. And yet, we are finding them. Small, rocky worlds, potentially habitable planets. Statistical analyses based on Kepler data suggest there could be as many as 40 billion Earth-sized planets in the habitable zones of Sun-like and red dwarf stars in our galaxy alone. 40 billion places where liquid water might exist, where life, as we understand it, might have a chance. And that's just one galaxy. There are an estimated 2 trillion galaxies in the observable universe. The numbers become absurd, meaningless in their magnitude. There are more potentially habitable planets than there are grains of sand on all of Earth's beaches. Perhaps more than there are stars in the sky. And yet, we have not found life. Not a single confirmed biosignature, not a signal, not a structure, not a whisper. The Fermi paradox haunts us. If life is common, if intelligence is possible, where is everyone? The paradox is named after physicist Enrico Fermi, who reportedly asked during a casual lunch conversation in 1950, "Where is everybody?" Given the age of the universe, the number of stars, the apparent ease of interstellar travel for a sufficiently advanced civilization, why haven't we seen any evidence of alien life? There are many proposed solutions to the paradox. Perhaps life is rarer than we think. Perhaps the step from chemistry to biology is incredibly unlikely. Perhaps Earth's history involved a series of improbable events: the formation of the moon from a giant impact, the development of plate tectonics, the evolution of photosynthesis that rarely occur elsewhere. Perhaps intelligence is even rarer. Perhaps the step from simple life to complex multicellular life is difficult. Perhaps the evolution of intelligence requires specific conditions that rarely occur. Perhaps civilizations inevitably destroy themselves. Perhaps there's a great filter ahead of us, some existential threat that all technological civilizations encounter: nuclear war, climate catastrophe, artificial intelligence gone wrong, nanotechnology disasters, something that prevents civilizations from spreading across the stars. Or perhaps the great filter is behind us. Perhaps the difficult step was already past: the origin of life, or the evolution of complex cells, or intelligence itself. And we're one of the lucky few who made it through. Perhaps the universe is full of life, but space is simply too vast. Perhaps other civilizations exist, but they're too far away to detect, separated from us by thousands or millions of light years. Perhaps they're quiet. Perhaps they've learned that broadcasting signals is dangerous. Perhaps the universe is a dark forest, full of predators, and survival depends on silence. Or perhaps we're looking in the wrong way. Perhaps intelligence doesn't develop radio technology. Perhaps advanced civilizations use communication methods we haven't conceived of. Quantum entanglement, gravitational waves at frequencies we haven't explored, neutrino beams, technologies we can't imagine. Perhaps civilizations exist for such brief periods that the chance of two existing simultaneously and within detection range is vanishingly small. The universe is 13.8 billion years old. Human technological civilization is barely a century old. If other civilizations follow similar timescales, the overlap window is tiny. We don't know. And that uncertainty, that vast question hanging over everything we do, is both terrifying and exhilarating. Space is patient. It has waited billions of years. It can wait longer. There are structures in the universe so large, they should not exist. The Hercules Corona Borealis Great Wall is a superstructure of galaxies spanning approximately 10 billion light-years. 10 billion. If you tried to cross it at the speed of light, it would take you longer than the current age of the universe. It is the largest known structure in the observable universe. And according to our cosmological models, it shouldn't be there. The cosmological principle, one of the foundational assumptions of modern astronomy, states that the universe should be roughly homogeneous on large enough scales, that if you zoom out far enough, matter should be evenly distributed. There should be no structures larger than a certain size, because gravity hasn't had enough time since the Big Bang to pull them together. The theoretical limit based on the speed of gravity and the age of the universe is roughly 1.2 billion light-years. Structures larger than that shouldn't exist. The Hercules Corona Borealis Great Wall is roughly 8 times larger. How do you measure something so vast? You can't see it directly. It's too diffuse, too spread out. Instead, astronomers use gamma-ray bursts as tracers. Gamma-ray bursts are the brightest explosions in the universe, visible across billions of light-years. They occur when massive stars die or when neutron stars collide. By mapping the positions of many gamma-ray bursts, astronomers can trace the distribution of galaxies, because GRBS occur where massive stars form. When they plotted the positions of bursts, detected over many years, a pattern emerged. A vast concentration in a specific region of the sky. Too many bursts too close together to be random. A structure, a wall of galaxies stretching across 10 billion light-years. Perhaps our models are incomplete. Perhaps the early universe was lumpier than we thought, with larger density fluctuations that seeded larger structures. Perhaps dark matter behaves in ways we haven't accounted for, clustering more strongly than our simulations predict. Or perhaps the structure isn't real. Perhaps it's a statistical fluctuation, a random clustering that looks significant, but isn't. More observations are needed to confirm. Or perhaps the universe is trying to tell us something, that our assumptions, our elegant theories, our careful models are approximations of a deeper truth we haven't yet glimpsed. There are other massive structures. The Sloan Great Wall, discovered in 2003, spans 1.37 billion light-years. The CFA-2 Great Wall, found in 1989, stretches roughly 700 million light-years. Laniakea, the supercluster that contains the Milky Way, spans 500 million light-years and contains about 100,000 galaxies. Laniakea, Hawaiian for immeasurable heaven, is our cosmic address. The Milky Way is part of the Local Group, which is part of the Virgo supercluster, which is part of Laniakea. And Laniakea is being pulled toward the Shapley supercluster, which is even larger. These aren't isolated objects, they're part of the cosmic web, that vast filamentary structure of galaxies and dark matter stretching across the universe. The cosmic web is one of the most beautiful structures in nature. Galaxies cluster along filaments like beads on strings, with enormous voids in between. The filaments connect at nodes, where massive galaxy clusters form. It looks organic, like neurons in a brain, like blood vessels in an organism, like mycelium in soil. Patterns that emerge from simple rules playing out at different scales. After the Big Bang, matter was distributed almost uniformly, with tiny density fluctuations imprinted by quantum effects during inflation. These fluctuations were literally quantum mechanical uncertainties, blown up to cosmic scales. Over billions of years, gravity amplified those fluctuations. Slightly denser regions attracted more matter, becoming denser still. Less dense regions emptied out, becoming voids. Computer simulations of cosmic structure formation, starting from the initial conditions and evolving forward in time according to the laws of gravity and fluid dynamics, reproduce the cosmic web remarkably well. The simulations showed dark matter collapsing into filaments, with galaxies forming where those filaments intersect. But the existence of structures as large as the Hercules Corona Borealis Great Wall suggests we might not fully understand how this web formed. Either the early universe had larger fluctuations than predicted, or gravity acts differently on these scales. Or our observations are somehow incomplete or biased. We are very good at finding patterns, at constructing models, at predicting how the universe should behave. But the universe does not read our textbooks. It does not conform to our expectations. And every so often, it surprises us. There are objects visiting us from other star systems. In October 2017, astronomers detected something unusual. An asteroid moving through the inner solar system on a trajectory that couldn't be explained by any known gravitational interactions within our system. They named it Oumuamua, Hawaiian for scout or messenger from afar arriving first. It was the first confirmed interstellar object ever detected passing through our solar system. A visitor from another star system, traveling through the galaxy for millions or billions of years before happening to pass close enough to the Sun for us to notice. Its trajectory was hyperbolic. Unlike asteroids and comets, native to our solar system, which orbit the Sun in ellipses, Oumuamua was moving fast enough to escape the Sun's gravity. It came from the direction of the constellation Lyra, passed through the inner solar system, and departed towards the constellation Pegasus. And it was strange. The object was elongated, cigar-shaped or pancake-like, tumbling end over end as it traveled. Its dimensions were estimated at roughly 400 meters long and 40 meters wide, far more elongated than any asteroid or comet we'd seen before, and it accelerated as it moved away from the Sun. This is normal for comets. As they warm up near the Sun, ice sublimates, releasing gas that acts like a rocket engine, slightly changing the comet's trajectory. But Oumuamua showed no signs of outgassing, no coma, no tail, nothing that would indicate it was a typical comet. So what was pushing it? Theories ranged from mundane to exotic. Perhaps it was a comet with unusual composition, nitrogen ice or carbon monoxide ice, which sublimates without leaving a visible coma. Perhaps it was a fragment from a larger object, shattered by collision in another star system. Or perhaps it was artificial. The idea was explored briefly by the Breakthrough Listen project, which used radio telescopes to search for any signals emanating from Oumuamua. They found nothing, no radio transmissions, no evidence of technology. But the suggestion lingered. Harvard astronomer Avi Loeb proposed that Oumuamua might be a light sail, a thin reflective sheet pushed by starlight, perhaps a piece of debris from an alien spacecraft, or even a functional probe. The scientific community was skeptical. Extraordinary claims require extraordinary evidence, and the evidence for an artificial origin was circumstantial at best. Natural explanations, while unusual, were more plausible. But the debate highlighted something important. We don't actually know what interstellar objects should look like. Oumuamua was the first we'd ever seen. We had no baseline for comparison. In 2019, we found another one, 2I/Borisov, a comet from interstellar space with a visible coma and tail. It looked like a normal comet, just arriving from elsewhere. How many of these objects pass through our solar system? Estimates suggest that at any given time, there might be dozens of interstellar asteroids and comets within Neptune's orbit. Most are too small or too far away to detect. They're messengers from other star systems, fragments of planetary formation around distant suns. Each one carries information about the chemistry and conditions in its home system. If we could catch one, analyze it directly, we might learn about planets and protoplanetary disks light years away. We might even find organic molecules or hints of processes that lead to life. Projects are being proposed to intercept and study interstellar objects. Fast spacecraft that could launch quickly when a new object is detected, rendezvous with it, and send back detailed data. Because these visitors are rare opportunities. Samples from other star systems delivered to our doorstep. Windows into planetary systems we could never reach. And perhaps, occasionally, one of them will be artificial. A probe from a distant civilization. A message in a bottle drifting through the cosmic ocean. We'll probably never know if Oumuamua was such an object. It's gone now, too far and too dim to observe. But we're watching, waiting for the next visitor, and wondering what it might tell us. And there are stars that dim in ways we cannot explain. In 2015, astronomers noticed something peculiar about a star called KIC 846-2852, better known as Tabby's star, named after astronomer Tabitha Boyajian, who first brought attention to its unusual behavior. The star dims, irregularly, dramatically, sometimes by as much as 22%. No regular pattern, no predictable cycle, just sudden, deep dips in brightness that last for days or weeks, then return to normal. This is not how stars behave. Planets cause dips when they transit their stars, but those dips are regular, predictable, and small. An Earth-sized planet might block 1% of its star's light. A Jupiter-sized planet might block 1 or 2%. But 22%? You'd need something enormous, something the size of a large planet or larger, passing in front of the star. But planets orbit regularly. They don't cause random, unpredictable dimming. Comets were suggested. A swarm of comets broken up by gravitational forces, creating a debris cloud that occasionally passes in front of the star. But the dimming pattern doesn't fit. The dips are too deep, too irregular, too long-lasting. Some proposed a protoplanetary disk, but the star is too old for that. It's a mature F-type star, well past the age when it should have a debris disk. And then there was the suggestion that captured everyone's imagination. What if it was artificial? What if an advanced civilization had built a megastructure around the star? A Dyson swarm, perhaps? A collection of solar collectors orbiting the star, harvesting its energy. As the collectors moved in their orbits, they would irregularly block the star's light, creating exactly the pattern we observe. The idea was intoxicating. Evidence of alien engineering, a civilization so advanced it could harness the energy of an entire star. SETI turned their telescopes toward Tabby's star. They searched for radio signals, laser pulses, any indication of technology. They found nothing. No signals, no evidence of artificial origin. More observations followed. Astronomers studied the star's light in different wavelengths, looking for clues. They found that the dimming was stronger in blue light than in red light. This suggested dust, tiny particles that scatter blue light more effectively than red. So perhaps it is a debris cloud after all. Perhaps the star recently captured material from a passing object, or perhaps there was a collision in the system, creating a cloud of dust that slowly orbits the star in a chaotic pattern. But we don't know for certain. The mystery isn't fully solved. Tabby's star continues to dim unpredictably, and we continue to watch, looking for patterns, searching for explanations. It's a reminder that even in our own galaxy, even among stars we've catalogued and studied, there are phenomena we don't understand. Behaviors that don't fit our models. Mysteries waiting to be solved. And perhaps, just perhaps, one day we'll point our telescopes at a star and find something that can only be explained by intelligence, by engineering, by another civilization reaching out across the cosmos, building structures so vast they block starlight. We haven't found it yet, but we're looking, and there are objects so bright they shouldn't exist. Quasars, quasi-stellar radio sources. When they were first discovered in the 1960s, they appeared to be stars, but their spectra were bizarre. Emission lines shifted far into the red, indicating they were receding from us at tremendous speeds. If they were that far away, moving that fast, they had to be extraordinarily distant. And if they were that distant, they had to be extraordinarily bright. Brighter than entire galaxies. Brighter than 1 trillion suns. How could something that bright exist? Eventually, we figured it out. Quasars are not stars. They're the actively feeding supermassive black holes at the centers of very distant galaxies. As matter spirals into the black hole, it forms an accretion disk, heating to millions of degrees, glowing so brightly it outshines every star in the galaxy. The most luminous quasars emit more than 1,000 times the energy of the entire Milky Way. And that energy comes from a region smaller than our solar system. The black hole itself might be only a few light hours across, the distance from the Sun to Neptune, yet it's outputting more energy than billions of stars. The efficiency is staggering. When matter falls into a black hole, a significant fraction of its mass is converted into energy through the process of accretion. It's more efficient than nuclear fusion, more efficient than any power source we know. If we could somehow harness a black hole's accretion power, we'd have access to energy densities that make fusion look primitive. But quasars raise questions. We've found them at incredible distances, corresponding to times when the universe was less than 1 billion years old. How did supermassive black holes, millions or billions of times the mass of the Sun, form so quickly? There shouldn't have been enough time. Even if the first black holes formed from the first stars, and even if they accreted matter at the maximum possible rate, they shouldn't have grown so large so fast. Perhaps they started larger. Perhaps in the early universe, massive clouds of gas collapsed directly into black holes, without forming stars first. Or perhaps black holes in the early universe could accrete faster than the Eddington limit suggests, somehow avoiding the radiation pressure that normally limits their growth. We don't know. But every quasar we observe is a window into the early universe, a glimpse of cosmic adolescence when galaxies were still forming and black holes were growing rapidly. And they're beautiful. In images from powerful telescopes, quasars appear as brilliant points of light, surrounded by the faint glow of their host galaxies. Beacons shining across billions of light years, their light traveling for most of the age of the universe to reach us. When we observe a quasar, we're seeing it as it was billions of years ago. By now, in the present moment at that location, the quasar has likely faded. The black hole has consumed most of the available gas. The brilliant accretion disk has dimmed. The galaxy has settled into a quieter state, much like the Milky Way. But we see it as it was, blazing, active, fierce. A reminder that the universe was once more violent, more energetic, more dramatic than it is today. There are particles arriving from space with energies that shouldn't be possible. Cosmic rays. Not rays at all, but particles, mostly protons, traveling through space at nearly the speed of light. They strike Earth's atmosphere constantly, billions of them every second, creating showers of secondary particles that rain down on the surface. Most cosmic rays come from supernovae. Exploding stars accelerate particles to tremendous energies, flinging them into space. These particles travel through the galaxy for millions of years, bouncing off magnetic fields, gradually losing energy. But some cosmic rays are different. Ultra-high energy cosmic rays. Particles with energies so high, they seem to violate the laws of physics. In 1991, a detector in Utah recorded a cosmic ray with an energy of about 50 joules. That might not sound like much, but remember, this is a single subatomic particle, a single proton carrying the kinetic energy of a baseball thrown at 100 kilometers per hour. The particle was traveling so close to the speed of light that time dilation effects were extreme. From the particle's perspective, the entire visible universe was compressed to a few hundred meters. It could have crossed the galaxy in minutes, subjective time. Where did it come from? What could accelerate a particle to such energy? Supernovae aren't powerful enough. Even the most energetic supernova explosions can't accelerate particles to these extremes. You'd need something more violent, something more energetic. Perhaps gamma ray bursts, the most energetic explosions since the Big Bang. Perhaps the jets from supermassive black holes. Perhaps colliding neutron stars or black holes. Or perhaps something we haven't imagined yet. Some process, some mechanism, operating on scales we don't understand. There's another puzzle. According to theory, ultra-high energy cosmic rays shouldn't be able to travel very far. They should interact with the cosmic microwave background, colliding with photons and losing energy. This is called the GZK cutoff, named after the physicists who predicted it. The cutoff means that ultra-high energy cosmic rays should only come from relatively nearby sources, within about 50 million light-years. Beyond that distance, they should have lost enough energy to fall below the ultra-high energy threshold. And yet, we detect them. particles with energies above the GZK cutoff, apparently arriving from beyond the limit. Either they're coming from sources closer than we think, or there's something wrong with our understanding of how cosmic rays interact with the CMB. Or perhaps they're not protons at all. Perhaps there's something more exotic: magnetic monopoles, strangelets, relics from the early universe, particles that don't interact with the CMB the way we expect. We don't know, but we're building larger detectors covering vast areas of desert and ice, trying to catch more of these rare, ultra-energetic particles, trying to trace their paths back to their sources. Each one that arrives carries information about the most violent processes in the universe, about the extreme physics operating at energies we can never achieve in our laboratories. They are messages written in the language of high-energy physics, and we are slowly learning to read them. We have heard sounds from space. Not sounds exactly. Space is a vacuum. Sound waves cannot travel without a medium, without molecules to vibrate and transmit pressure waves. But electromagnetic waves can. Radio waves, plasma oscillations, magnetic field vibrations, and these can be converted into audio frequencies translated into something our ears can interpret. In the 1970s, the Voyager spacecraft recorded the electromagnetic environment of Jupiter. The planet's powerful magnetic field, strongest in the solar system besides the sun's, interacts with charged particles from the solar wind and from its volcanic moon Io. When converted to sound, it produced eerie whistles, crackling static, and deep, resonant tones. The sound of a planet's magnetosphere, singing. These are called chorus emissions and whistler waves. Charged particles spiraling along Jupiter's magnetic field lines emit radio waves at specific frequencies, modulated by the particle's energy and the field's structure. When translated to audio, they sound almost musical, like birdsong, like whale calls, like something alive, singing in the dark. Each planet has its own voice, its own electromagnetic signature. Saturn sounds different. Its rings produce faint radio emissions as ice particles collide and exchange charge. Its moon Enceladus sprays water vapor into space from geysers at its south pole, and that vapor interacts with Saturn's magnetic field, creating a subtle hum. Uranus, with its tilted and offset magnetic field, produces irregular, chaotic emissions. Neptune's magnetosphere resonates with waves driven by the solar wind, creating patterns that shift and change. Earth has a voice too. The interaction between the solar wind and our magnetosphere creates radio emissions detectable from space. To an alien astronomer with the right instruments, Earth would sing. And by listening to these signatures, we can learn about planetary magnetic fields, atmospheres, the charged particle environments surrounding them. And then there is the cosmic microwave background. The afterglow of the Big Bang, the oldest light in the universe, carries within it tiny fluctuations. Variations in temperature of 1 part in 100,000, imprinted when the universe was only 380,000 years old. These fluctuations represent the seeds of all structure, the regions that would eventually collapse into galaxies, clusters, and superclusters. Scientists have converted these fluctuations into sound. By mapping the temperature variations to audio frequencies, they created a sonic representation of the early universe. The result is a deep, resonant tone, a cosmic hum, the sound in a sense of creation itself. It's a low-frequency drone with subtle variations representing the density fluctuations. If you listen carefully, you can hear the pattern that would eventually become the cosmic web, the blueprint of the universe, encoded in sound. The loudest tones correspond to regions of slightly higher density. the seeds of future galaxies, the quieter tones to regions of lower density. Together, they form a symphony of creation. And there are stranger sounds still. In 2003, NASA's Chandra X-ray Observatory detected sound waves emanating from a black hole in the Perseus galaxy cluster. Not metaphorical sound, actual pressure waves traveling through the hot gas surrounding the black hole. The note it produces is a B flat, 57 octaves below middle C, the deepest note ever detected from an object in space. That note has been playing for 2.5 billion years. The mechanism is remarkable. The black hole's jets push against the surrounding gas, creating ripples that propagate outward like sound waves in air. Those waves have been oscillating for billions of years, creating cavities in the gas visible in X-ray images. By measuring the spacing of those cavities, astronomers calculated the wavelength, roughly 30,000 light-years from crest to crest. From that, they determined the frequency and the equivalent musical note. B flat, 57 octaves below human hearing, a note so deep that its period is measured in millions of years. If you could hear it, if your ears could detect such low frequencies, the entire galaxy cluster would be resonating with that single, sustained tone. A cosmic bell, ringing slowly through the darkness. The Perseus cluster is not alone. Other galaxy clusters also show evidence of sound waves driven by black hole outflows. These waves may play an important role in preventing the hot gas from cooling and forming stars, regulating galaxy growth. Space is not silent. It is filled with sounds we cannot hear, signals we are only beginning to detect. And each one carries information about magnetic fields, about plasma dynamics, about the fundamental processes governing the universe. We are learning to listen. There is a point in space, roughly 13 billion light-years away, where we are looking at the universe when it was only 5% of its current age. The light we see from that distance has been traveling for most of the history of the cosmos. It left its source when the universe was still young, still forming its first galaxies, and it has been crossing the emptiness ever since. When we look at distant galaxies, we are not seeing them as they are now. We are seeing them as they were. We are looking backward in time. This is one of the profound gifts of astronomy. The speed of light is finite, roughly 300,000 kilometers per second, and so looking across space is also looking across time. The Andromeda Galaxy appears as it was 2.5 million years ago, when our ancestors were just beginning to use stone tools. The light from the center of our own galaxy left when anatomically modern humans first appeared, roughly 300,000 years ago. And the most distant galaxies, we see them as they were in the universe's infancy. The James Webb Space Telescope, launched in December 2021, has peered deeper than any instrument before it. Its large mirror and infrared sensitivity allow it to detect the faint, red-shifted light from the earliest galaxies. Some of these galaxies existed just a few 100 million years after the Big Bang. They're more massive, more structured, more mature than our models predicted. One galaxy, JADES GS Z140, existed just 290 million years after the Big Bang. It contains hundreds of millions of stars already formed. How is that possible? Where did the stars come from so quickly? The puzzle deepens with each new observation. JWST keeps finding galaxies that shouldn't exist yet. Galaxies that formed too early, grew too fast, organized too quickly. Either our models of galaxy formation are wrong, or the early universe was very different than we thought. Perhaps the first stars formed faster than expected. Perhaps they were more massive, burning brighter and faster, seeding their galaxies with heavy elements within a few million years. Perhaps dark matter played a more active role. Perhaps the density fluctuations in the early universe were larger than we thought, creating gravitational wells that pulled gas together more efficiently. We don't know yet, but every observation from JWST is rewriting textbooks. And that's exciting. It means we're learning. It means the universe still has surprises. And as we look deeper, we approach a limit. The cosmic microwave background represents the farthest back we can see with light. Before that point, roughly 380,000 years. After the Big Bang, the universe was opaque. Before recombination, the universe was too hot for atoms to form. Free electrons scattered photons constantly, preventing light from traveling in straight lines. The universe was like a fog, glowing but impenetrable to vision. Then, as expansion cooled the universe, electrons and protons combined to form neutral hydrogen. Suddenly, photons could travel freely. The universe became transparent. That moment of transparency, the surface of last scattering, is what we see as the cosmic microwave background. It's the oldest light in the universe, stretched by expansion into microwaves. We cannot see beyond it with telescopes. The earlier universe is hidden from us, but we can infer what came before. Gravitational waves, ripples in space-time itself, can travel through conditions that would block light. Projects are underway. LISA, the Laser Interferometer Space Antenna, will detect low-frequency gravitational waves from space. Pulsar timing. Arrays use the galaxy itself as a detector, monitoring the precise timing of pulses from dozens of neutron stars. If we detect gravitational waves from the early universe, we could see all the way back to the first moments. Perhaps even to inflation itself, the rapid expansion that occurred in the first fraction of a second. But even if we succeed, we'll still be left with questions. What came before the Big Bang? Our equations break down at the singularity. Time itself may not have existed before. Asking what came before might be meaningless. Or perhaps time is not what we think. Perhaps the universe is cyclical, expanding and contracting forever. Perhaps it's one bubble in an infinite multiverse. Perhaps the Big Bang was a transition, not a beginning. We don't know. And that's okay. The edge of knowledge is where the most exciting work happens. There are moments late at night when the weight of all this becomes almost unbearable. To know that we are living on a small planet, orbiting an ordinary star, in a galaxy of hundreds of billions of stars, in a universe of trillions of galaxies. To know that we are made of elements forged in dying stars. That every atom in our bodies was created billions of years ago in stellar furnaces. To know that the ground beneath our feet is moving, the planet spinning at 1,000 kilometers per hour, the solar system orbiting the galactic center at 200 kilometers per second, the galaxy falling through space toward an attractor we'll never reach. To know that everything we have ever known, every person, every civilization, every thought, has occurred on a mote of dust suspended in a sunbeam. And yet, here we are, conscious, aware, capable of wonder. The universe is not required to make sense to us. There's no reason our brains, evolved for survival on an African savanna, should comprehend quantum mechanics or general relativity. And yet, we do. With mathematics and observation, with patience and creativity, we have begun to understand the cosmos. We have measured the age of the universe, traced the evolution of stars, mapped the cosmic web, detected gravitational waves, photographed black holes. We are a species that looks up, that asks why, that builds telescopes and sends them into the dark, not because we must, but because we cannot help ourselves. Curiosity is woven into us as deeply as DNA. And the universe has given us just enough time, just enough stability, just enough intelligence to begin understanding it. We exist in a narrow window. The universe had to be old enough for heavy elements to form, for planets to coalesce, for life to evolve. But not so old that all stars have died, that the cosmic microwave background has faded, that distant galaxies have receded beyond reach. We are living in the stelliferous era when stars dominate. It will last trillions of years. But within that era, we exist at a special time. A time when we can still see the cosmic microwave background. When distant galaxies are visible. When the universe's history remains accessible. In the deep future, civilizations arising on planets around long-lived red dwarfs will see only their own galaxy. No CMB, no evidence of the Big Bang, no way to know they live in an expanding universe. We are lucky to exist when we do, to have the tools we have, to ask these questions and find answers. There are billions of years ahead. The sun will burn for another 5 billion years. Long before that, Earth's oceans will boil away as the sun brightens. Life, if it survives, will move outward, to Mars, to the moons of Jupiter and Saturn, to other star systems, perhaps other galaxies. Humanity's story is still being written. If we survive the next few centuries, climate change, nuclear weapons, pandemics, artificial intelligence, the universe opens before us. Red dwarf stars burn for trillions of years. A civilization harnessing such a star could endure for timescales that make human history a heartbeat. And there are trillions of stars in our galaxy alone. The potential is staggering. We could become a spacefaring species spreading across the galaxy, establishing colonies on millions of worlds. Or we could develop differently, building megastructures, uploading consciousness, becoming something we can't yet imagine. The future is unwritten, and the discoveries will continue. New telescopes will peer deeper. New detectors will listen for gravitational waves from the early universe. New spacecraft will visit Europa, Enceladus, Titan, searching for life. We will find things we cannot yet imagine, phenomena that challenge understanding, questions we didn't know to ask, because that's what the universe does. It surprises us. Every time we think we understand, the universe reveals something new, something strange, something that forces us to rethink everything. The history of science is a history of surprises, of overturned assumptions, of paradigm shifts. We thought Earth was the center. Wrong. We thought the Milky Way was the entire universe. Wrong. We thought the universe was static. Wrong. We thought expansion was slowing. Wrong. This process will never end. The universe is infinite in complexity, infinite in depth, infinite in subtlety. We could study it for 1 billion years and still find new mysteries. So where does that leave us tonight? Still here, still watching, still wondering. We have explored rogue planets drifting in darkness and stars fleeing their galaxies at impossible speeds. We have witnessed the birth of heavy elements in colliding neutron stars and heard the deep song of a black hole echoing through a galaxy cluster. We have found radio bursts from billions of light years away, arriving without warning or explanation. We have mapped enormous voids where almost nothing exists and traced the filaments of the cosmic web stretching across the universe. We have measured the invisible, dark matter holding galaxies together, dark energy pushing space apart. We have seen stars dim in patterns that defy explanation and detected particles with energies that shouldn't be possible. We have found thousands of worlds orbiting distant suns, worlds of diamond and glass and lava, worlds orbiting dead stars, worlds drifting alone through interstellar space. And we have looked back in time, to the edge of the observable universe, where galaxies shine as they were when the cosmos was young. All of this strangeness, all of this beauty, and we have only just begun. The universe is 13.8 billion years old. It will exist for trillions of years more. We are living in its youth, in an age when stars still burn brightly, when galaxies still collide and merge, when the cosmos is still rich with structure and light. One day, that will change. The stars will exhaust their fuel. The galaxies will drift apart. The universe will grow cold and dark and empty. But not yet. Not for a long, long time. And in this brief, shining moment, we are here, we have consciousness, we have curiosity, we have the ability to look up at the night sky and wonder. We are made of atoms forged in stars. We are the universe becoming aware of itself. And in that awareness, we find something profound, not answers necessarily. The universe is full of mysteries we may never solve. Questions that may have no answers or answers we cannot comprehend. But in the search itself, in the act of wondering and questioning and exploring, we find meaning. We find purpose. We find connection to something larger than ourselves. We are small, unimaginably small. A species on a planet orbiting an ordinary star in an ordinary galaxy. Our entire history from the first humans to now is a blink in cosmic time. And yet, we matter. Because we are the ones asking questions. Because we are the ones trying to understand. The universe doesn't care whether we exist. It doesn't notice our struggles or celebrate our achievements. It simply is. But we care. We notice. We celebrate. And perhaps that's enough. To be here in this moment, aware of the vastness around us, aware of the strangeness, aware of the beauty. To know that above us, beyond our atmosphere, beyond our solar system, beyond our galaxy, there are wonders we can barely imagine. Phenomena so extreme they challenge our understanding. Processes operating on scales so vast they make our planet look like a grain of sand on an infinite beach. And to know that we, against all odds, are here to witness it. What a gift. What an extraordinary, improbable, precious gift. Thank you for being here tonight, for listening, for wondering, for allowing yourself to drift, just for a little while through these vast and quiet places. The universe will continue long after we're gone. The stars will keep shining. The galaxies will keep spinning. The cosmic web will keep expanding. But we were here. We looked up. We asked questions. And in doing so, we added something to the universe that wasn't there before. Consciousness, understanding, wonder. We are a way the cosmos knows itself. And that is no small thing. So keep looking up. Keep asking questions. Keep wondering. The universe is strange. It is beautiful. It is full of mysteries. And we have only just begun to listen. Safe travels, friend. Wherever you are, under whatever sky, may you always find wonder in the darkness. Good night.